Welcome to the fifth lecture in the series on ChatGPT for developers. In this video, we will explore how to make API requests using the openAI Python library to perform named entity recognition or NER. We have already examined various payload JSON parameters such as model, messages, and temperature in detail. Now we will delve into the max tokens parameter, and we will also gain an understanding on how tokenization works. In the previous lectures, we learned about using the OpenAI API endpoint for chat completions, but we were making a post request. There is also another option of using the OpenAI Python library directly. This is a more convenient way to interact with the API. To use the OpenAI Python library, you need to first import the OpenAI module. Then you will need to set your secret key. Next, you can call the create function, which is found in the completion class in the OpenAI package. This function is responsible for making the API request and to generate the completions. Then we will provide the necessary parameters in the function call, and this will determine the behavior of the completion. There are 4 different modes in ChatGPT: completion, chat, insert, and edit. So far, we have focused on text completion or single-turn prompts. For text completion, we use the complete mode in the completion class, and we make a complete request using the create function. On the other hand, we also have chat completion. This involves multiple back and forth conversations, but this falls under the chat mode. Each mode utilizes a different set of models. For example, the complete mode can be achieved using the text DaVinci 003 model, but not the GPT 3.5 model. This was covered in lecture 2. Language models are proficient in various NLP-based tasks like sentiment analysis, language translation, named entity recognition or NER. NER is a technique in which we will identify entities like person names, locations, organization, product, date, and much more within the natural language text that we are providing. The NER will provide the entity label along with the corresponding text as output. In the example, Alex lives in India. Alex is tagged as a person entity and India is tagged as location entity. In text completion, for performing NER, the text DaVinci 003 model is suitable. A well-crafted prompt clearly states what task is to be performed and also the desired format of the output. In this case, the prompt instructs the model to perform NER and specifies that the model should be presented in the form of a table with the headings, entity, and type. To ensure precise output, a low temperature of 0.2 is set. In the payload JSON, when we specify max tokens as 30, it refers to the maximum number of tokens in the completion underscore tokens field in the response JSON. The completion tokens represent the generated text tokens that was returned by the model as part of the completion. By setting max tokens, we can limit the length of the generated output from the model. The output is obtained in the form of a table, and in this case, the completion token is 26. And additionally, the prompt contains 20 tokens. Now let's explore how these token counts are calculated. Help is available on the OpenAI platform at platform.openai.com. To access the API reference, navigate to the left pane, select completions, and then select create completions. This will provide a comprehensive list of all the API parameters that are available for text completion. To view the maximum token limit for each model, navigate to the documentation section of the OpenAI platform, select models, and then choose GPT 3.5. Since the DaVinci model belongs to the GPT 3.5 model set, in the documentation, you will find information about the token limits and other details specific to the model. To gain insight into the token count calculation for a prompt, visit the link platform.openai/tokenizer. The link is given in the description below. This page allows you to input your prompt and observe the resulting token count. The tokens are displayed in color-coded format, indicating how they are split and segmented within the text. By exploring this tool, you can get an understanding of tokenization and how the prompt is represented in terms of tokens. We can also copy the output text and verify the token count. When calculating tokens in this manner, we typically estimate that one token corresponds to approximately 4 English characters. 1,000 tokens will be equivalent to around 750 English words. The pricing details for OpenAI's API usage are based on the number of tokens processed. Generally, the pricing is structured for every 1,000 tokens with varying rates depending on the specific usage and plan. The encoding process includes tokenization, where the input text such as Alex lives in India is split into individual words or subword units. These words or tokens are then assigned numerical values or encoded representations. This encoding step enables the language model to understand and process the text as numerical input during the training phase and the inference phase. During tokenization, it is worth noting that words can be split into subwords, and this can increase the total number of tokens. For example, the word perform might be split into subwords like per and form during the tokenization process. This subword splitting helps the model to handle variations and to capture more nuanced information within the text. But this also contributes to a higher token count when we compare with the original word count. We can verify the token count using various methods, but to calculate the token count programmatically, one approach is to use the OpenAI Python library's tick token package. When the text string is passed to an encoder, it performs both tokenization and encoding. The encoder tokenizes the text by splitting it into tokens, then assigns a unique token ID to each token. This process converts the text string into a list of token IDs. The list of token IDs represent the encoded version of the original text string. For example, here it is shown for P50K base encoding. The tokenization and the number of tokens can vary depending on the encoding technique employed. Different encoding methods use different distinct rules for tokenization. This results in variations in the number of tokens generated from a given text string. Indeed, the encoding techniques can differ based on the specific model being used. For example, GPT 3.5 Turbo model employs CL100L-based coding technique. This technique may exhibit differences in tokenization compared to other models. By examining the examples, you can observe the variations in the tokenization patterns. For example, in CL100K base, perform is tokenized as perform, whereas in P50K base, perform is split into per and form. These variations can result in different token counts, and they also provide insight on how the different models handle text representation. To use the tick token package, we import tick token. We get the encoding for a specific language model called text DaVinci 003 using encoding for model functions. This has information about the tokenization scheme and the vocabulary for that particular model. For example, here the encoding scheme is P50K base. The encode function in the tick token library is used to tokenize the input text. This takes a text string as input and it returns a list of token IDs that represent the tokens in the text. Each token ID corresponds to a specific token in the model's vocabulary. The resulting token ID will be a list of integers that represents the token ID for each token in the input text. The code can be found in GitHub and the link is given below. To find the number of tokens in a list, we can use the len function. By applying len to the list of tokens, we can find the token count. Finally, we use the decode single token bytes for each token. And this is used to decode the token IDs back to their corresponding tokens in text form. It iterates over every token ID in the token ID list, and then it decodes each token using the decode single token bytes function. By applying this code, you will get a list of tokens that were originally present in the input text before tokenization. Each token will be represented as a string. The initial part of this lecture series is designed for beginners, wherein it provides foundational knowledge. In the next video, we will demonstrate writing a simple code using the LangChain framework for text completion. This will help us to gain hands-on experience and understand how to implement text completion using LangChain framework in a more straightforward manner. Thank you.